All right, hi guys. So I've posted review lectures. Um, there's no video associated with the review lecture. It's just slides. It's some content that I believe you should definitely know before we start the next half of this semester, where this next half is going to be introducing you to data structures and algorithms. Yeah, if you really do need to know what objects are, what classes are, you need to know inheritance, interfaces, generics. This stuff all gets used in data structures and algorithms. So please go through those review slides and make sure you know that material. Okay, so this lecture is going to talk about introduce you to data structures. And then we'll get started into a particular data structure called a linked list. Okay, so if we look at the slides here, a data structure is a way of organizing and performing operations on data. Operations performed on a data structure include, generally speaking, accessing or updating some type of stored data, searching for a specific data amongst a whole collection of data, inserting new data, and removing existing data. And so how do we make a data structure? Well, it's those tools that we've been going over in the first half of this class. Usually a data structure is comprised of a class or classes, methods, and interfaces. And so you've actually already used a data structure before called an array list. And so yeah, an array list is a class, right? You know it implements some interfaces and it has tons of methods that you should have used already. Okay, so moving on. There are many common data structures that we're going to look at in this particular course. And these include the linked list, which is what we're covering today, a stack, a queue, a hash table, and if we have time by the end of the semester, we'll briefly talk about trees, although it's not as, that's more so a data structure as a CS310 material. So before we get started with linked lists, it's important to recall what a reference type is. Linked lists heavily use the concept of a reference type. If you don't understand this concept, then you're going to have a hard time understanding how a linked list works. So, to refresh your memory, a reference is a variable type that refers to an object. And so it can be thought of as storing the memory address of an object. And if you looked at if you've watched the memory video, an object's memory resides on the heap, right? And so basically the reference is an address to that memory on the heap. Okay, so linked lists. There are two types of this linked list data structure. One of them is called a singly linked list, and the other is called a doubly linked list. We'll start with the singly linked list. It's just simpler in terms of understanding the basics of what a linked list is and how it works. But basically, a singly linked list is a data structure made up of a series or list of consecutive nodes. A node typically has holds some sort of data and a pointer or a reference to the next node. The first node in a singly linked list is called the head, and the last node in a singly linked list is called the tail. So we'll go ahead and look at an example. So you can see each of these square boxes is a node. Each node holds some sort of data and has a next reference variable that refers to the subsequent node. And so it kind of creates this sort of chain, right? And you can see the very first node is denoted as the head, and the very last node is denoted as the tail. And so here's some explicit code to help understand what the node class is. So a node class, you can see I'm using Java generics here. This is just because in this case, we don't really know what type the data might be. So we're just calling it E for now. And this is a very common practice when working with nodes, just to make your data structures very scalable. And you'll notice that we also have a next variable, and its type is node E, right, using the same generic type E. So this is the same type as the class that we immediately reside in. Why is that? Well, next we'll point to or reference another node of the exact same type. And then this right here is just a constructor initializing the data. And so here's how how you might create a linked list, but this is the naive method. You can see I have a class main here. I have the main method, and then basically I just go down the line and create all of the nodes. So here's my head node. I clearly start with a value of 5, node 1, the value of 35, node 2, 105, node 3, value 12, and then I create the tail node with the value of 50. And then I set the appropriate next reference variables. So head.next will equal node 1. Node 1.next will equal node 2. Node 2.next will equal node 3. Node 3.next will equal the tail. And then this creates basically your chain, the linked list, right, chained together. And so here is the resulting linked list. You can see we start off with the head. The head's data was 5. Its next was set to reference node 1. And now we have node 1, its data was 35. Its next was set to reference node 2. Node 2's data, 105. Node 2's next set to reference node 3. Node 3's data is 12, and its next variable set to the tail. And the tail's data is 50, and you'll notice the next is set to null. That's because there's nothing else beyond the tail, right? The tail is the end of the linked list. So you will find that having the next set to null sometimes problematic, but we'll figure that out later. So the previously mentioned code to create the linked list is considered naive because it's not scalable. We hard-coded that to a specific number of nodes with specific values. A linked list should be able to dynamically handle any number of nodes within reason, of course, right? You don't, if you add enough nodes to, fill up all your memory, of course, you'll have issues, but, within reason, dynamically handle any number of nodes. And another issue is that the previous code existed solely in our main method. And what we want to do is put our linked list in a class to help with code reuse. So that way, every time that you want to use a linked list, you're not doing what we did in this previous slide where we create a bunch of nodes like this and so on and so forth. And this makes sense, right? The array list that you use is a data structure, and that data structure is in an array list class. And so here's the start to our linked list. You'll see I used the Java generics class called linked list. I specify a head node and a tail node, and I specify a constructor for my linked list where I just set head equal to null and tail equal to null. This is the default condition for the linked list. It just means that there's nothing in it. It's it's empty. So yeah, this is a start, but now how do we add nodes to our linked list data structure? And as it turns out, there's a lot of common operations that can be formed on a linked list, and each of these operations have their own issues. In this case, we're talking about the add operation, adding to the linked list. But there are many other ones. And we're going to look at a few of these, not all of them, but quite a few of them, the main ones. So we'll start with the append operation for a singly linked list. It inserts a new node after the list's tail node. And Java calls this operation add last. And so yeah, you'll notice that append really is just an abstract concept of an operation. Add last is Java's actual name for this abstract concept. But they both basically mean the same thing. You're adding to the end of this data structure, or in this case, this linked list. So after the tail node, add a new node. But there's an issue. Appending the node addresses a common algorithmic question: what is the behavior when appending to a list that is empty versus when the list is not empty? As it turns out, the different conditions require different behavior to handle them. So we'll go ahead and look at and see what it takes. So when appending to an empty list, or linked list in our case, if the list's head pointer is null, in other words, it's empty, the list's head and tail now point to or reference the new node. And to append to a non-empty list, if the list's head pointer is not null, in other words, there's at least one element in the list, then the tail node's next pointer must reference the new node. Then, and an order matters here, then the reference to the tail node must change to be the new node. Right, so we'll go ahead and look at an example for both appending to an empty list and appending to a non-empty list. I'll go ahead and draw the example on the whiteboard here. So, case 1, appending to an empty list. And so in this case, what is in our linked list? Well, I'm not going to write out linked list entirely. I'll just abbreviate it to be LL. So L. Well, we have a head and a tail. Head, tail. But, as is the case with an empty linked list, they both reference null. That means that there's nothing in the list. So, I'll go ahead and write null here. And the arrows represent the head references null and the tail references null. And the operation we're doing here is append. So I'll go ahead and put append. And what is it we're appending? Well, we're appending a new node. So let's go ahead and create a node. So this box here will represent a new node. Now every node, as we know, contains some sort of data, as well as a next variable that references the next node. So we'll start with the data. Data. I'll just give it a value of 27. And then the next variable, next. This new node doesn't know anything about the linked list, so its next variable can't currently reference anything, so it's set to null. Okay, so if we look at the description of how to append to an empty list, it says the list's head and tail now point to, or in other words, reference the new node. What this means is instead of referencing null, the head and the tail now reference the new node. And so this node is now both the head and the tail, which means that the list only contains a single item, one node. Now the next variable inside of this single node still remains null because there's nothing for it to point to. There's nothing, since it is only one node, there's not a second node for it to point to. And this is a pretty trivial case. The non-trivial case is appending to a non-empty list, which is case 2. So we'll go ahead and look at that. And so our linked list is actually going to start off with 3 nodes. So here we are. Here's the first node. Here's the second node. And here's the third node. And so they all need some data and next variables. So data, next, data, next, data, next. And we'll go ahead and give them some values. So the data for the first one we'll say is 5, the data for the next one is 32, and the data for the last node will be 70. And this first node will be the head, right, as is the case with the structure of a linked list. The first node is always the head. And the last node is always the tail. So we'll put tail down here. Now you'll notice that this middle node doesn't have a name, like a head or a tail or new node or node 1 or anything like that. And that's okay, because if you remember, right, the next variable is a reference type. Now what is the next variable referencing? Well, it's referencing the address of this node's memory. And so I could put here, some address like, 0x, 112234 or something like that, right? But just for keep things simple, I'm just going to draw a dot. And then I'm going to draw an arrow to where this next variable references, which is in this case this unnamed node. And the same will be the case for this unnamed node's next variable. Now I could put something like it references tail here, but just to keep things relatively consistent, I'm just going to also do a dot with an arrow. And then there's nothing past or beyond the tail nodes, or beyond the tail node, and so because of that, its next variable is null. Okay, and so what are we doing here? Well, we're appending. So here's our append operation. And what are we going to append? Well, we're going to append a new node. So let's go ahead and create a new node. The new node will have some data. And the next variable, whose default value is null. So if we look at the steps of what to do, it says the tail node's next pointer or variable, this guy, must reference the new node. This guy. Then, and I highlighted then there because order matters here, the reference to the tail node, which is just the name here, the tail name, must change to be the new node. This guy. And that makes sense, right? Because if we're appending to the end of the linked list, this new node is now at the end of the linked list. And according to our rules, the tail should be at the end of the linked list. So essentially what we're saying is update the new node to become the tail. So we'll start with the first step. The tail node's next pointer must reference the new node. So in our abstract example here, I'm just going to erase the null. And in this case, I'm going to replace it with a dot and an arrow. And now that represents referencing this new node. I'll show you what this looks like in code. And then the next example says, then the reference to the tail node, this guy, must change to be the new node. So in our case, we're basically using arrows to represent referencing. So let's erase the current arrow and give it a new arrow to reference the new node. Here. And now everything works, right? Our chain exists between the different nodes. The head is the first node and the tail is still the last node. And we've appended this new node. All right. So that's it for case 2. And that's it in terms of the cases you need to worry about for appending to a linked list. We'll go ahead and look at the code for that now. As you can see here, right, my class linked list, this is the same code as before. So assume, all of this still exists. But now we have this add last method. You notice that the add last method takes in some sort of type E. Note that E here is not a node, E is the type of data that the node holds. And so you can see the very first thing we do in this add last is, so we create the new node. This node here, this node variable I've created, was this new node that we are appending. And so really what this would be is add last, and the data would be 27. So the input E here would be 27. And so we do an if-else statement, right? That represents the two different cases. The if statement represents case 1. If head is equivalent to null, then we know the linked list is empty. And according to case 1, if the linked list is empty, the head and the tail should equal the new node. Now, if this is not the case, if the head is not null, then we know we have at least one node inside of our linked list. And if that's the case, then we have to follow steps for case 2, a non-empty list. The non-empty list said to adjust the current tail's next variable to reference the new node. So here's the current tail's next variable, and it should now become equivalent or reference the new node. Then what we need to do is update the tail to become the new node, to reference the new node. And so now tail references this new node. Now you might be wondering, well, that's weird, right? Why is it we can change the tail's why do we change the tail's next variable to be the new node? Then we change the tail itself to be the new node. This is where you have to remember, tail is just a reference type. And so tail was referencing this object's memory. And so when we said tail.next equals this node, we were referencing this memory. But then when we said tail equals node here, which is changing the reference from here to here, tail now references this object's memory. So looking at the next operation for a singly linked list, there's the prepend operation. This is very similar to append. It inserts the new node before the list's head node. And Java tends to call this operation add first. This is very similar to the append operation, and the cases that we're concerned with are the same. Is the list empty, or is the list not empty? So prepending to an empty list, not surprisingly, is the same as appending to an empty list. If the list's head pointer is null or empty, and the list's head and tail pointers reference, then the list's head and tail pointers should reference the new node. And when I'm saying head pointer, head and tail pointer, really what I'm talking about is the variable name, right? The head and tail variable name, or the next variable name. And then the second case is similar to append, where we're prepending to a non-empty list. So if the list head pointer is not null, in other words, there's at least one element in the list, then the new node's next pointer, or variable, must reference the head node. And then, once again, then, all caps, bolded, highlighted, because order matters here, then the head node must reference the new node. So I'll leave the code for this method to you, but I'll go ahead and run through an example. I'm not going to do the prepend to an empty list, because this example is the exact same as for the append, but I will do the prepending to a non-empty list. And so what you can see what I've done here, right, is I'm just using the last example's nodes to save time. And here's my current linked list. I have the head references this node here, whose data is 32. And this node's next variable references the next node, this guy, whose data is 70. And this guy's next variable references the next node, who happens to be the tail. And the tail's data is 27, and there's nothing beyond the tail, therefore the next variable for the tail is null. And the operation we're doing this time is prepend, and here's the node that we're prepending. Now, you'll notice I switched it up so that the new node now is at the front. This just helps with the example, because that's what prepend means, right? We're adding a node to the front of the linked list. So yeah, we'll go ahead and follow along with the instructions. The first step says the new node's next pointer, so the new node's next pointer or variable must reference the head node. So that's this guy. So we'll go ahead and do that. And similar to the append example, we'll get rid of the null, and we'll say, okay, next now references the head. Then the head node must reference the new node. So for a similar reason as to why the tail node needed to change references, the head node needs to change the reference, because this node is no longer at the beginning of the linked list, and the head must be at the beginning of the linked list. So in order to fix this, we change the head's reference. We say, okay, head no longer references this object, instead head will reference this object, or this node. And now we have successfully prepended to the linked list. The new node is now the head node of the entire linked list. So on to the next operation. We have the insert at operation that inserts a new node at a provided index. Now Java calls this operation add, and this add operation or method has two input arguments. The first is called index and is of type int, and the second is called element and is of type e. Now we've seen this element of type e before. If we look back a few slides, we can see here for the add last, which was the append method, our input to this method was e of type e. And so e in this case really is as element, And so what is it? Well, it's the data that gets stored inside of the node. In this case, you can see that my data is just a number, right? But it really could be anything. Now, what is the index? And this brings up an interesting point, right? Index is what we used to, or indexing is what we use to access elements within an array. And so an index is really like a location. And so you can view the nodes in a linked list similarly to the cells within an array, where the very first node in the linked list might have location or index 0, and then the subsequent node might have location 1 or index 1, the next node index 2, and then the next node index 3. And so now you might be able to say, okay, well, for example, what is the data at node of the node that is at location or index 1? And you would say 32. Or more specifically, in this case, you want to add a new element at a particular index. So let's say we want to add a new node that contains the data of element at index 1, this guy. Well, as you can see, there's already a node here. And so the question becomes, how do you handle that? And so if we look at the next point here, the element at the desired index and subsequent indices must get shifted over. So what this means is, if we say we want to add a new node at index 1, and there is already a node and subsequent nodes, then the node at index 1 and subsequent nodes must get shifted over, meaning the location of the node currently at index 1 will become index 2. And the node currently at index 2 must move to index 3. And likewise, with the node at index 3, it must become the node at index 4, so on and so forth. And then what that leaves is basically an empty spot at index 1, and that's where the new node is to be inserted into. Note that this is different. Zybooks talks about an insert after, which inserts it after a specific node. This operation, this insert after operation, is similar to the insert at. They are slightly different. Now, as is the case with any of the operations, right, there are scenarios or cases that we need to worry about. So for the insert at, there are two particular scenarios we have to worry about. The first one is the empty list, which we've already seen. And the second is inserting into the middle of the list, which will require shifting. As it turns out, shifting for a linked list is easier than shifting for an array. So we'll go ahead and look at the first case. So inserting into an empty list. We're going to assume that the input index is 0, and that's because it will keep the index bounds within a reasonable region for this particular case. And so if the list's head pointer is null, which means the list is empty, and the index to insert at is 0, then the list's head and tail should then point to or reference the new node. And this is exactly the same way to handle this case as for prepend and append. Now, the non-trivial case is inserting into the middle of the list, which will require shifting. Conveniently, shifting is built into linked lists in terms of handling inserting nodes. So assuming that the input index is within the valid range of the linked list. If the list head pointer is not null, meaning it's not empty, then we set the new node's next variable to reference the previous node's next variable, or reference. Then set the next pointer, or variable, at the previous index's node. And so I'm saying previous index's node here, and all that means is just the previous node. So for example, if we're talking about node 1, the previous node to node 1 would be node at index 0. Or for example, if we're at index 3, the previous node at index 3 would be index 2. And so yeah, we set the next pointer or variable at the previous index's node to reference the new node. Now, we have to assume that we have access to the previous node. And so we'll go ahead and call that a variable reference similar to head and tail, but we'll call it prev node. And so we'll go ahead and look at an example of this. I'm going to go ahead and adjust the current example we have on the board here. Okay, so this is our current linked list, right? We have our head here, the data is 5. I'm going to keep the indices here just to represent their locations. And the next pointer or reference, right, or variable references the next node, this guy, whose data is 32 and whose next variable references the next node, who happens to be the tail, whose data is 70 and whose next variable references null or nothing because there's nothing after the tail node. And so the operation we're doing here is the insert at. We'll go ahead and make a method call though, just to show you what it looks like. So we'll say add 127. Right? And so what this is saying is add a new node to our linked list. The data should be 27, and it should be added at or inserted at index 1. And so if we look at the steps on how to do this, I'll go ahead and create the new node right here. The new node doesn't have an index yet because it has not been added into the linked list. Now, if we look at the first instruction, it says set the new node's next variable, so this guy, to reference the previous index's node's next reference. So the previous index, in this case, we're saying index 1. So the previous node to index 1 would be index 0. So the new node's next variable should reference basically the node that it's replacing. And you could say that the node that it's replacing is the next variable, or what is referenced by the next variable of the previous node. And so essentially all we're really saying here is the next variable for this new node should now reference this node right here. Then set the next pointer or variable at the previous index's node, so this guy, to reference the new node. So we basically change where the arrow is pointing. So instead of pointing at the 1, we point at the new node. And so now if we look, the chain in our linked list has changed. And so really, the index has automatically changed for us. The shifting just naturally occurs by inserting the new node into its appropriate location by adjusting the next references. And so this node's index is now 1, this node's index is now 2, and this node's index is now 3. Now, I'll go ahead and clean this up a bit to show you what the end result looks like in a more clean linked list. So this is the same linked list that I just changed. I just made it clear that the new node was inserted into the first index. So we're not going to worry about the code for this. It's a little bit out of the scope of this class. You are more than welcome to try and program this yourself. You do have the tools capable of doing it. But what you really need to know is you need to understand the abstract concept of what's going on. How adjusting the next variables, what they're referencing, will affect the chain in our linked list. So if we look at the next operation, we have the remove at operation. This removes a node at a specific index location. And this is similar to Java's remove given an input of an index. And then once again, this is different from Zybook's example where they do a remove after, which refers to removing a node after a specified node. So there are now 4 cases, though, that we need to worry about when doing this. There's the empty list, there's removing the list's head node, removing the list's tail node, and then removing in the middle of the list. So the trivial case, removing from an empty list, is pretty easy to solve. If the head and tail nodes point to null, then the list is empty, and then therefore there's nothing to actually remove. And so we're done. I'm not going to show that as an example up here. That should be somewhat intuitive. If there's nothing there, then you can't remove anything. Now, a little less trivial, removing at the list's head node. If the index to remove is 0, then it's the head node that we want to remove. And so you can do this by setting the head reference, this guy, to the head's next pointer, or itself's next pointer. So basically what we're saying is, the head currently references this node, but what we need to do is set it to this node's next, which currently references this guy. And so we'll go ahead and just do that, right? We'll say, okay, head, you no longer reference this very first node, you now reference whatever this first node's next variable is referencing, which is this node. And so that begs a question, what happens to the old head node, this guy, in memory? And this is why we talked about garbage collection in one of the other lecture videos. There's nothing that now references this node in memory. So its reference count is now 0. And due to its reference count being 0, it gets garbage collected. And so there's no need to actually do any deleting of nodes. It is more so about adjusting references. And so since nothing references this node anymore, it's now gone. And you can automatically, once again, the indices to the linked list are already handled for us. So this is now 0, this is 1, and this is 2. So removing at the list tail node, if the index to remove is equal to the length of the list minus 1, so the end of the list, then the desired node to remove is the tail node. And to do this, we have to once again assume that we have a reference to the node preceding the tail node. We'll call this the previous node. Since this node right here is the node preceding the tail node, we'll call it pre node. And so the idea is to set the tail node reference to become the previous node reference. And then we set the previous node's next pointer or variable to reference null. So we'll go ahead and do that. We adjust the tail node reference to be equal to the previous node's reference. Well, since the previous node is here, we say tail. You now reference this node. And then what do? We say set the previous node's next reference. So here's our previous node. That's this guy. The next variable to reference null. Okay, so we get rid of this reference. And we'll just put null here. And once again, nothing now references this node here. And so what happens is it will get garbage collected. And so there's no need to actually do any erasing of this node. It just automatically will disappear. The erasing of the node, if you will, really is setting this next reference to null. So for the next condition, I'm going to repopulate our linked list example here. And so once again, the operation is remove. So we're going to remove in the middle of the list. We'll say, let's remove the node at index 1. So remove 1. And so if the index to remove is a valid location in the middle of the list, which index 1 is in this case, then we need to access two different nodes. The node to remove, which in this case will be index 1, and the node preceding the node to remove. So we're going to assume that this node to remove at index 1 is called node to remove. And that the node preceding the node to remove is once again called prev node. We're going to assume we have access to it. Now, conveniently, the previous node is also called head, but this won't always be the case. So prev node. That's pretty sloppy. We'll try it again. Prev node. Right, so this guy references here, and this guy references here. And so the idea is set the previous node's next pointer or variable. So that here's the previous node's next pointer or variable to reference the node to remove's next pointer. So if we look at the node to remove, its next variable or pointer references this node right here. And so what we're saying is this previous node, its next, should reference this guy's next, which is this guy. Which means we're going to want to change the arrow to reference here. Then we set the node to remove its reference to null. And by its reference, what I mean is this node to remove reference. Because once again, this is a reference type similar to tail and head in previous node. And so we'll go ahead and do the example here. So we say previous nodes next should now be set equal to node to removes next, which is this guy. So essentially this arrow should no longer point to the node to remove, it should point to or reference the next node. And so why do we want to set the node to remove's reference to be null? And that once again has to do with the garbage collection concept. Nothing now references this node's memory. And so because of that, it will get garbage collected. Now you might ask, well, okay, but this node's next variable still references another node. And that's actually not an issue here. This next variable, referencing this next node here, only increases this node's reference count, not this node's reference count. And so this node's reference count is currently 0, which means it gets garbage collected. And so we can adjust the reference arrow now to be a little cleaner. And the indices automatically fix themselves. So the indice for this node is now 1 and this node is 2. So the shifting is automatically solved. And then we're done. Now, once again, in a lot of these operations, the cases, we've used something called this previous node, which is basically a reference to whatever the previous node at some desired index is. And we were just given this. But in reality, you're not just given the previous node, you have to go find it. And shortly here, we'll cover how you go find the previous node, as well as the node to remove. So we'll go ahead and move on. That's the end of the operations for singly linked lists that we'll cover. We will get back into the other, if you remember at the very beginning, there was a second type of linked list called a doubly linked list, and we'll briefly look at that. Most of the doubly linked list is somewhat out of the scope of this class, but we can still cover it abstractly and understand what's going on at a higher level. We'll go on to the next slide. So we're going to take a brief aside and talk about collections. Collections relate to data structures, which relates to the linked lists that we were just looking at. And so the question is, how do we know what operations or methods a data structure should include? Notice the difference between should include, right? As well as opposed to knowing what they are. Yeah, we know what the methods are for, let's say, an array list or a linked list now. But what dictated that those methods should even exist in the first place? And so Java's answer to this is the collections framework. This framework is basically telling anyone who is going to create data structures that are part of this collections framework what methods and operations it must have. And so according to Java, a collection represents a group of objects known as elements. And the collections framework defines the starting point for data structures that will be working on a collection, which is basically every data structure. If you think about it, your linked list holds a bunch of data. Now, how it holds it is using nodes and referencing the next node and all of that stuff. But nonetheless, it holds a bunch of data. It has a bunch of operations on that data. And the same goes for an array list. An array list holds a bunch of data and has a bunch of operations that work with that data. And so essentially what you can say is a linked list or an array list is a collection of data or objects, if you will. And they call these objects elements. And so essentially what you might say is that each of these data variables are elements. And now that sort of makes sense now, considering if we look back at the insert at operation, if you notice, one of the input parameters is called element of type E. So that's where they got element from, is in the collections framework, they refer to data as elements. And so we can go ahead and take a look at Java's collections framework. Escape. There we go. We'll go ahead and look at Java SE 11. Say linked list. And we can see the inheritance here. And if we go up the inheritance tree and we look at the abstract collection here, click on this, and it says all implemented interfaces, and we'll see a collection interface. And this is what we're talking about here, is this interface, the root interface in the collection hierarchy. A collection represents a group of objects known as its elements, and a bunch of other information, right? But what you'll notice here is, so it's an interface, right? None of these methods are implemented, but it prescribes or says that if you're going to be a part of this collection framework, you must implement this interface. And if you implement this interface, you must implement these methods. And so this is how, some of these methods should look familiar, right? You see add all, clear, contains, remove all, size, toArray, right? These are some familiar methods. And they've been dictated by this collection interface. And then what happens is this interface gets inherited or implemented by, for example, abstract collection, which is an abstract class. And then this abstract class gets inherited by, abstract list, which gets inherited by, let's say array list here. And so this is how, you enforce data structures to have to implement certain methods or recommended methods. And it keeps everything consistent. So the list interface defined within the Java collections framework represents a collection of ordered elements. Or not just a collection of ordered elements, but the base set of operations that a list data structure should have. A linked list is one of several data structures that implement this list interface. So we'll go ahead and look at the list interface real quick. Go back here, go back to abstract list, it should be one of these, here we go, list interface. And this list interface, you can see here under the description, an ordered collection, also known as a sequence. The user of this interface has precise control over where in the list each element is inserted. The user can access elements by their integer index, or in other words, their position in the list, and search for elements in the list. And so you can see it comes with a set of predefined methods. A lot of these you can see already match up with the collections interface, the add all, etc. except for there's some new ones, the of here. There's a replace all, and there's a sort method here. And so this interface is big for lists in particular, which is basically the only two data structures we really know right now, an array list as well as a linked list. And so that list interface is big in defining the methods that lists should have. And so there's other useful data structures in Java's collections framework, other than the linked list or array list. But for now, we'll go back to the linked list. So in the insert at and remove at operations, there was a key proponent that made our lives easy. And it was having access to the previous node. This is what I was talking about where it's given to us. But accessing such a node isn't actually free. It's not just given to us. We have to find out how to find the previous node. And so what it takes is traversing a linked list. But in order to understand traversing a linked list, we first have to understand the concept of an algorithm. Because yes, traversal, or in other words, what I mean by traversal is, finding or searching is the basis of an algorithm. So if we look, an algorithm describes a sequence of steps to solve a computational problem or perform a calculation. So a computational problem specifies an input, a question about the input, and a desired output. And so here's an example. Given this computational problem, the input is an array of integers. The question is, what is the maximum value in the input array? And in the output is the actual maximum value, which in this case is 92. And so the algorithm is basically talking about, well, how do we solve this here? How do we solve this computational problem? And they write pseudocode, right? You see some value max, it's set equal to the initial value inside of the array. And then you go through a loop. You're going to start at index 1 and loop until you hit the end of the array. And what you do is you keep checking if the value at the current index is greater than the current maximum value. If this holds true, then that means you need to update the maximum value to be the new maximum value. And once you've looped through the entire array, then you will have found the maximum value, and that's what you return in this find max method or function. So we'll go ahead and look at the linked list traversal algorithm. And so what it needs to do is visit all the nodes in the list once and performs an operation on each node. A common traversal operation prints all list nodes. And so here's our computational problem, right? The input is a linked list. The question is, can all of the nodes in a linked list be visited? And the desired output is to print all of the nodes in the linked list, showing that they can indeed be visited. And so the algorithm starts by assigning a node reference called cur_node to the list's head node. So it's creating another reference, just like the head node, and it's just called cur_node. And cur_node, current node, you start it off by beginning at the beginning of the linked list. And so then the idea is to loop through all of the elements in the linked list by setting the current node or the cur_node reference to its own next pointer or variable. And you print the elements as the linked list is traversed, or you, by traversal, right, it means going from one node to the next node to the next node to the next node, etc. And the stopping condition for this algorithm is when the current node eventually becomes null. That means you've reached the end of the linked list. And so here's the pseudocode. I have my current node, and I set it equal to the head. I have a while loop, and so if you remember, right, the stopping condition is when the current node eventually becomes null. And so that's what this is right here. While the current node is not null, print the current node's data. And this is the updating, this is the actual traversal through the linked list. So we say current node is equal to current node dot next. And so that's this right here, setting the current node reference, this guy, to the current node's next pointer, this guy. And so if we look at our current example here, I'm going to go ahead and remove some of the jargon on this. Remove the previous node here. And essentially, we have a current node. I'm going to add in another node here, just to make it a little more visible. And so we said our current node is equal to the head, which is here. So we'll say, I'm going to set current node up here. And currently it references this node. So while we enter the while loop, while current node is not null, well, current node is not null, it currently references this node, the head node. We're going to print its data. So we print its data, we'll put the data down here, 5. Then we say current node is now equal to its own next variable. Well, since current node points to this node right here, this node's next variable references the next node. So we adjust where current node is currently referencing to be the next node. And then we continue with the loop. So current node currently is still not null. So we're going to go ahead and print its data, which is now 27. And then we're going to once again adjust current node's reference to be its own, to reference its own next variable. And so in doing so, what we're saying, right, is, okay, current node, change your reference to be whatever your next is referencing, which is the next node, this guy. So we'll go on to the next node. Once again, current node is not null. We'll print current node's data, which is now 32. And then once again, change its reference to go on to the next node, which also happens to be the tail node. And so, once again, current node is not null. We print its data, which is 23. And then we adjust current node to be equal to current node's next. Well, current node's next is null. So what we do is we say, okay, current node now references null. And then we'll see that the while loop immediately fails, right? It says current node is actually null, so we exit the while loop, and we're done. So we've now printed everything in our linked list. And that is the traversal algorithm for a linked list. It is continuously, it's taking a reference variable and going through, traversing, or visiting each node in the linked list by using the next reference variable. What if, right, this particular algorithm is just printing the contents of a linked list. But in our case, we can use this to find that previous node. that was magically given to us before. So, I should update the indices here. 1, 2, 3. So, let's say we want to remove at index 1. Or I'm sorry, let's say we remove at index 2. If you recall, if we go back to the slide, remove in the middle of the list, this is the condition, and it needed a node to remove and a previous node. And so our algorithm slightly changes. What we need is a node to remove reference variable similar to the current node reference variable that we had, and a previous node reference variable. And what they're going to do is side by side traverse or visit the linked list until the node to remove is found. So we're looking for 2, and so the idea is here's my node to remove. Here's my previous node. Currently, previous node is, we'll say it's null, and my node to remove will begin at the head, just like the cur node in our traversal example. And so, similar in this algorithm, right? We check, is what the node to remove currently pointing at index 2? And the answer is no, it's at index 1. And so the idea is you want to move on to the next node using a similar methodology to this traversal algorithm here. And so we adjust where node to remove currently references, and it goes on to the next node, this guy. Now, the trick to this is that the node to remove is actually followed by previous node. Previous node will always be the previous node to the node to remove, which means previous node is now set equal to this guy. And so continuing on with our algorithm, node to remove is looking for 2, but currently is at 1. So this is not what we want. So move on to the next node. So node to remove now references the node at index 2. And previous node must follow the node to remove. So now it references index 1. And then once again we make that check, right? Node to remove is looking for the node at index 2. Is node to remove at index 2? Yes. So we've now found the node to remove, and the previous node is at the correct location. And then we continue with the removing in the middle steps as we did before. Except for now, we weren't just given previous node and node to remove, we found it ourselves. And this same logic can be applied to the other cases where we need the previous node, where it was just given to us. So now we'll talk about the doubly linked list. It's similar to the singly linked list, except now each node has a pointer or a reference to the previous node as well as the next node. So the doubly linked in this case refers to having 2 pointers or links to the previous and next nodes, respectively. This allows a doubly linked list to be bidirectional, which means in our case, right, our singly linked list is single in its direction. It can only go next, 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 but it can't go backwards. That's why we needed this previous node. And the doubly linked list, by having another reference pointer that goes backwards, solves this problem. So let's go ahead and take a look at what this looks like. So I'm going to adjust what's inside of our nodes now. I'm going to say our nodes, you have a next, which points to the next node, and a prev, which represents a reference to the previous node. In this case, for the head, it will be null. And then this node's next will reference the next node. And this node's prev, or previous node, and I'm not going to start from the dot here, I'm just going to start just for simplicity's sake, this side,
The second one, so I'll try.
references the previous node. And this pattern follows for all the nodes remaining in the linked list. And so this, as you can see now, it's bidirectional. You can traverse the linked list by calling the next, or accessing the next variable, going one direction. And then you can go backwards by accessing the previous variable to go to the previous node. So suddenly the need for finding a previous node is eliminated. It's just given to us by holding on to a reference to the previous node. And so there's 4 common doubly linked list operations that we've already seen that are similar to the singly linked list operations. There's append, prepend, insert, and remove. The append operation for a doubly linked list inserts a new node after the tails node. Java tends to call this operation add last. This is the same as for a singly linked list, and the implementation is nearly identical, except now you also have to worry about fixing your previous node that a node contains. So once again, the cases are the same. Appending to an empty list. If the list's head pointer is null, in other words, it's empty, then the list's head and tail now both must reference the new node. I'll go ahead and show what that looks like with the doubly linked list. So your head and your tail point to null. You have a new node. Your new node has data, a next variable, which is currently set to null, and a prev variable that's also set to null. And that's because, right, you don't know your next or your previous in this new node. And the idea is your head and tail references must now reference the new node, which is extremely similar, in fact identical to how you would handle it in a singly linked list. The non-trivial case is when you already have items in your linked list, in other words a non-empty list, and now you have to fix not just the next reference, but the previous reference too. And so to start, right, the next always points to the next node, and the previous always points to or references the previous node. And the very first node is always the head node, right? And the very last node is always the tail node. And so we'll go ahead and add the new node. Data will be 7. Next will be is null, or yeah, null. We're about to change the previous, I'll leave it there. So the idea is, if we follow along in the instructions, the tail node's next pointer must reference the new node. So the tail node, this guy, is referencing currently this guy, right? And its next pointer, or variable, this guy, must now reference the new node, this guy. So we'll change this, it's no longer null. It now references the new node. Then we must point the new nodes, or change the reference of the new node's previous pointer, or variable, this guy, to reference the tail node, this guy. So pre is now set to reference this guy. Then the reference to the tail node must change to be the new node. So if we look currently, right, the appended node here is now actually at the end of the linked list. And to follow the linked list's requirements, the tail must be at the end of the linked list. So we have to change what the tail is currently referencing to now be this new node. So moving on, there's a prepend operation, just like the singly linked lists. It inserts the new node before the list's head node. Java calls this operation add first. And it's similar to the append operation. There are two cases to be concerned with. The behavior when the list is empty versus behavior when the list is not empty. The prepend to an empty list is the same as the append to an empty list, which has basically been universally the same across the board. The head and tail pointers now reference the new node. Once again, I don't feel a need to show this example, it's already been shown. So prepending to a non-empty list is similar to append, except for now you work with, instead of the tail, you work with the head. And so the idea is, if the list isn't empty, then the new node's next pointer must reference the head node. Then you have to point or change the reference of the head node's previous pointer to be the new node. And then you have to adjust the head node to be the new node because it was no longer following the requirements of a linked list. So we'll look at this example. I'm just going to erase these references here. So we'll say this is our linked list here, right? We have our head, we have our tail, right? And here's our 3 nodes in our linked list. This is currently null. And this right here will be our new node. And so the idea is the new node's next pointer, or variable, this guy, must reference the head node. So we draw a reference arrow. Then we have to point or change the reference of the head node's previous pointer or variable, this guy, to be the new node, this guy. And then the head node must reference the new node because now the requirement for the linked list has been broken. The head must point to the very first node in the linked list. And that is prepend. So, of course, there are more methods to the doubly linked list where, the same ones as in the singly linked list where, you have the insert at and remove at. And the idea is the same for all of them. You need to adjust not just the next reference variable, but also now this previous reference variable. Now, I'm not going to go into insert at and remove at because things start to get more complicated with the doubly linked list. That's some of the upside of a doubly linked list is that you no longer need that when searching for nodes. You no longer need that traversal algorithm in terms of a previous node following the current node that you're looking for. And that's because you have this built-in bidirectional functionality. The downside is now there's a lot of overhead for, when you add and remove nodes, you need to make sure you're managing both the next and the previous pointer. And so the insert add and the remove add are just, slightly more complex versions of the singly linked list. I think it starts to make things a little more confusing and is a little out of the scope of this class to learn specifically those methods. But you do need to understand the difference between a singly and a doubly linked list. So going on to the next slide, notice that when we insert an element into the middle of a linked list, we must first traverse the linked list in order to access that location. And this is a downside to a linked list data structure, especially when compared to an array list. So, if you think about the linked list, right, we needed to continuously call the next variable in order to get the next node. Whereas with an array list, which is implemented using an array, you can do just straight indexing and go directly where you want to. And there's no real traversal needed. If you wanted to go to index 5 in an array, you would just go to index 5. Whereas if you're going to index 5 in a linked list, of course you would traverse until you've reached the fifth node. At the same time, that sort of layout for a linked list also has some advantages, and it has to do with memory. So if we look at the next slide, so you can see that there's basically the left side, there's array list memory, and it functions basically similar abstractly as an array. You've got these consecutive cells, right, and inside of these cells you have values, and beneath the cells you have the indices representing those values, or representing the locations of those cells. And so you can see they're all right next to each other, right? If you know where the starting index is at, or at least the address to get there, right, then you know how to get the rest of the elements because they're all only going to be a set length apart. And so indexing into an array is very quick and efficient. Whereas if we look over at the memory, what it looks like with a linked list, notice how they're not consecutive here. They're actually fragmented across memory. They're not right next to each other. And so each of these blocks shows, a node, and inside of it is just perhaps the value or the data of that node. Now, there's a benefit to this fragmentation. There's actually two. So a linked list will always have as much memory as it needs. So what do I mean by that? Well, you're only going to have, you're only going to take up as much memory as you have nodes, and you're never going to have useless nodes that aren't doing anything. Whereas the same can't be said to be true of an array. An array, you allocate memory for it, but you don't necessarily fill it all up. In this particular example, we've filled up this array, but for example, what happens if the 4 wasn't here? And let's say the 3 wasn't here either. Only half of the array is full. Now, this may seem trivial to you now, but let's say the array has, a size or capacity of a million, right? And you only fill up 100,000 slots in there, you're wasting a lot of memory. It's just memory has been reserved for your array, but it's not actually being used. Whereas this could never be the case for a linked list. You will always, if your linked list has 10,000 items, it has 10,000 nodes, there's not more than 10,000 cells. And that brings up another point. A linked list, it's very easy to add another node, right? You just find some other spot in memory and you put the node there, and it's fine. Whereas an array, well, you're stuck, right? You must have consecutive cells, and so you start off with a set size, And if you want to go beyond that size, well, then you need to basically create a brand new array and copy all of the elements over, which the array list conveniently does for you, but that's inefficient. So that's just talking about the pros and cons between an array list and a linked list, and part of the reason why a linked list even exists if we already have an array list.